Well, good afternoon. It's 2:33, 3 minutes late getting started for differential equations class, but unfortunately I'm the only person in the room. When I got here and no one was here, I was a little early. I thought, well, I'll run down and make one last pit stop and a variety of things, and still nobody's here. So we'll go on and get started where we left off last time. And there are maybe one or two little announcements, but I'll wait till there's a body in the room to make those. So let's get the screencast-o-matic started. Oh no, I think I forgot to end. Oh, it's already started. Sorry. So let's go back to PowerPoint. This came up a different screen from normal. All right, so we'll get started from the current slide. And we're in Chapter 2, which is first order differential equations, Section 2.6, a numerical method, and we're on example 2, and this is another one of those fairly long, kind of drawn out problems, but let's see what we got with it. Consider the initial value problem. Here's y prime. Let me get my pen set up. Y prime is equal to 0.2 xy. Okay? Given the initial value, y of 1 is equal to 1, or at least a beginning value of that. It says use Euler's method to obtain an approximation of y of 1.5 using the first h is equal to 0.1 and then h is equal to 0.05, where h is the interval increase. Okay? So, if you remember Euler's method, and that's given at the top of this very page, y of n plus 1 is equal to y sub n plus h times f of xy. Okay? Well, x sub n, y sub n. Okay? Now, in our problem here, this is your f of xy, the 0.2 xy. Your y sub 1 is 1, and x sub 1 is 1. That's from your initial values. So we'll do y of 2, which is 1 plus 1, 2, is equal to y of 1, which is 1, plus your h. Oh, and let me write those down. We're first doing h of 0.1, and then later we'll do h of 0.05. Okay? So our h here first is, I don't need a parentheses, I don't think. Okay. 0.1 times f of 1, 1. So that'll be 0.2. Because x equal 1, y is equal to 1. Okay? So what does this give us? 1.02. There's your y sub 2. Your y sub 3, and by the way, this was for x sub 1 equal 1, y sub 1 equal 1. Now your x sub 2 is equal to 1.1, and your y sub 1 is equal to, y sub 2 is equal to 1.02. Okay, so y sub 3 is y sub 2, 1.02 plus 0.1 times your f, which is 0.2, times your x sub 1, 1.1, times y sub 1, 1.02. Okay. Now, I'm going to pause for just a moment just so I can go get a calculator, because I don't have a student here to do the calculations. I didn't bring one up. I have a little cheapie, but I'll be back in just a bit. Nope, wrong thing. Nope, wrong thing. All right, I'm back. Sorry, I stopped and said something to someone in the hall, so it took me a little longer than I intended. But anyway, I brought down my phone. It probably will run out of juice before the time's over with, but let's go for it. Okay? Okay. Calculator up. Good. Now, 1.02 plus 0.1 times 0.2 times 1.1 times 1.02 equal. I got 1.0424. And okay. Not getting the same thing the book did, which is sort of disturbing. Oh, I did. Right there. Yeah. Got it. Yeah, this is their y sub 3, which is 1 point. They got 1.02 for the y sub 1, y sub 2. Y sub 1 was 1. Y sub 2 was 1.02. Y sub 3 is 1.04244. Okay. Yeah. All right, the y sub 4. Okay, now x sub 3 is equal to 1.2, and y sub 3 was this 1.04244. Okay, so y sub 4 is at 1.04244 plus 0.1 times 0.2. 0.1 is a step. 0.2 is part of our problem. Our x is now 1.2, and our y is now 1.04244. Okay? And let's see what that gives us. I'm just going to keep that first number in there, plus 0.1 times 0.2 times 1.2 times 1.04244 equal 1.0675 is what they get. 1.06745856. Now that's way too many digits. I'm not going to carry that many always, but I'll write them down this time. So our y sub 5 is going to be that number, 1.06745856 plus 0.1 from our step size, 0.2 from the problem, and our x is now, x sub 4 is equal to 1.3. 1.3, and our x sub 4, our y sub 4 is going to be this number back here. Okay? So 0.2, okay, I was going to write this down, times 1.3 times this number here. Write it down if I can help it. Okay, so add to that, and 0.1 times 0.2 is 0.02. Saves myself some typing. Times 1.3 times 1.06745 856 equal. And I got 1.09521,248. Way too many digits, and they got 1.0952, and they stopped there, which is fine. Okay, now our y sub 6 is equal to that number there, 1.09521,248. 1.09521,248 plus, I'm just going to write the 0.02. Okay, sorry, my phone's going. Times 1.4, because that's my new x, and my new y is 1.09521,248. Let's see what that gives us. So it's that number plus 0.02 plus 1.4. No. Yuck. Just blew that. Okay. It's 1.09521,248 plus 0.02 times 1.4 times 1.09521248 equal 1.12587,843. Okay, they got in the book 1.1259, which is the same as I've got. Okay, now that's what they got. We did 5 steps. Okay, and this would be what our estimate is for 1.5. Okay, so that's where we begin. That would be that value. Okay, now they say to do the same thing with H 0.05. So what I'm going to do is leave my some of these down here, but I'm going to take off and erase so I can do some more. Okay, so this time we're going to do H of 0.05. Okay, and we'll use the same formula, same initial value, and things will start well there, and there, and there. Oh, I can't get it to erase. Okay, I think I'll erase most of what's left here. Okay. The reason I'm doing this is I want you to see how the answers vary, and we'll come back and do, I'm going to have to Well, I'm not getting it to erase anything. Oh, let me use my pen. That might work better. Okay, pick up a few loose ends here. Can't get that last spot to go. Okay. Now, our difference here is our initial value, y1 is 1, plus 0.05 times x, which is 0.2 times x, which is 1, times y, which is 1. So this is going to be 1.01. Okay. And that's it. That's our y sub 2. Our y sub 3 is going to be that 1.01 plus, now this time it's 0.05 times 0.2, so that's 0.1 times 1.05 times 1.01. Okay. Because our 0.0205 times 0.2 is 0.1. Okay. And then we'll put the previous ones in. So let's clear this and do a 1.01 plus 0.105 times 1.01. 1.1605. 11605. Let's see what they got. No, I did something wrong. O1 was that one. So 1.01 plus 0.105 times 1.01 equal. I'm not getting the same thing they did. Okay, 1.01 is what they got the first one. 1.01 plus 0.05 times 0.2 times 1.05 times 1.01 equal. I don't know why it wouldn't work the other way, but that's 1.02 0.020605. Okay? 1.020605 plus 'I know why it wouldn't work. That's 0. 0.020605 . 0. 0.020605 0. 0.020605 0. 0. 0.020605 0. 0. 0.020605 0. 0. 0.020605 0. 0. 0.020605 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0 0.01, not 0.1. Okay, that's why it didn't work. Okay, I think I did the plus. 0.01 times 1.1 times 1.020605 equal. Yuck, it didn't. 1.020605 plus 0.01 times 1.05 times 1.020605 equal 1.03. I think I typed something in wrong again. Let me try again. Yeah, this is aggravating. 1.020605 plus 0.01 times 1.1 times 1.020605. Nope. 1.020605. I have to watch every button. Equal 1.0318. That's right. 1.03183166. Okay, that's where I'll begin the next one. Okay, this time let me keep up with it. 1.1 and 1.15. Okay. Okay. So that plus 0.01 times 1.15 times 1.03183166 1.0437. Yeah. 1.0437. Well, I have 369772. Okay, 1.2. Okay, that was our number 5. Okay, all right, good deal. Next one would be that plus 0.01 times 1.2 times this number here, 1.04369772 equal 1.0562. 1.05622209. Okay. The next number would be this one plus 0.01 times 1.25 times 1.05 6222209 equal 1.694. Yeah, 1.069424871.3. Okay, so So this number plus 0.01 times 1.3 times 1.06942487. 1.0833, yep. 1.08332739. Okay, so we'll take that number and add to that 0.01 times 1.35 times 1.08332.739 equal 1.0980. Okay, 1.09, it's supposed to be a 9, 795.231. Okay. So add to that 0.01 times 1.4 times 1.09795231 equal 1.1132 1.1133 2364. And this will be at 1.45. Okay? So we'll take that number and add to that 0.01 times 1.45 times 1.11332364 and equal 1.295. Yeah, 1.1294664 at 1.5. Okay. So this time we got 1.1295 is what the book rounded to. And last time we got 1.1259. Pretty close, okay? We figure this one probably is a little more correct. And the thing about this one is, I'm going to, I think, delete this now. Save on my battery. Okay. In example 1, the one we did last time, the true or actual values were calculated from the known solution. We're dealing with example 2 now, though. All right. I'm not going to do all these calculations, but they do give us this. The relative error, okay, is given the absolute error. I'm going to, now, what do we mean by absolute error? The difference from that and the known value at each one of these data points for x, okay? Divided by the actual value. The absolute error is the difference in what we calculated and the known value divided by the known value, okay, if you know the value, okay? And to get the percentage relative error, then we'll multiply that by 100. This will give you a decimal number. Move the decimal 2 places to the right, and you get the percent error, okay? And if you look at the standing here, when at 1, we know those exactly. That is the exact value, so the absolute error is 0 and the relative error is 0. Earlier, 1.1, the actual value was 1.212. So our absolute error was 0.0012, which is relative error is 0.12%, which is very, very small, okay? But our 1.1 here, I'm using the table in the book, we're off by 0.0006, okay? That was this value here, okay? And there, our relative error is 0.06%, which is an even better number. You keep on going until the y sub 5, and I've forgotten to erase mine, was 1.1259, where the actual value is 1.1331. Relative error of 0.0073, very close, and percent error was 0.64%. Whereas with a step size of 0.05, the value we got was 1.1295, the actual value 1.1331, same as before, and the absolute error 0.0037, and that relative error is 0.32%. So about half of what the relative error was when you had double the step size. Okay. Now, they put in the book here what they call a caveat. Euler's method is just one of many different methods in which a solution of a differential equation can be approximated. Although attractive in its simplicity, Euler's method is seldom used in serious calculations. It's introduced here just to give you a first taste of numerical methods. We'll go into greater detail in discussing numerical methods that will give significantly greater accuracy, notably the fourth order Runge-Kutta method, referred to as RK4 method. That's over in chapter 9. Kind of doubt if we'll get there, but if we do, you'll see how that works. And then they talk about numerical solvers, a computer program written in either to implement or a numerical method or to render visual representation of an approximate solution curve fitting the numerical data produced by this method is called a numerical solver. And that's what they basically use in the book. And then they'll give numerical solution curves, and you'll see that also given in the book. Now, then they come up with a warning. Knowledge of the various numerical methods is not necessary in order to find the numerical solver. This solver usually requires a differential equation to be expressed in the form of dy dx as some function of x and y, just like we were doing. Okay? However, there can be some bizarre results if you happen to choose values that happen to give you some weird combination of answers. And they show in the book a not very helpful numerical solution curve. Nowhere close. Now the figure above that is the equation we were dealing with, I think, our Euler's method, which shows reasonable following, but the further out you get, the further deviation you get. But then the exact solution is given, and then the RK4, Runge Cutter, what's that called? Fourth order Runge Cutter method. At certain points, it fits exactly, and then sort of does a linear approximation between those points. So overall, it's a much better fit. Part of the reason for that, it makes it fit at certain intervals. In this case, it looked like 1, 2, 3, and 4. So it made for a much more precise solution. Well, that finishes 2.6. Again, homework exercises here would be number 1 if it's in the back, number 3 if it's in the back, any of the odds 5 through 9 if they're in the back, 11 if it's in the back. And that's all, very few in this section. There is the Chapter 2 review questions, and again, the odd numbers have answers in the back, or at least where they do, so you could do any of the odds 1 through 11. That would be probably pretty much the first section, 2.1, 13, that's covered I think in 2.2, you can check the things, 15, I'd say 15 or 17, 19, that's covers just about all the different methods we did. Any of the odds 19 to 25, 27 and or 29, 31 if it's in the back of the book, 33 if it's in the back of the book, and 35 or 37 if they're in the back, and 39 if it's in the back. Okay. Now we're going to skip Chapter 3 because if my memory's right, let's see, I should have it here. I don't think modeling was mentioned in the course description. Yeah. So we're skipping Chapter 3 and moving on. Now, Chapter 3 is not a bad one to look at. You'll find some pretty interesting things in there. For instance, Willard Libby is featured on page 86. If you want him as a paper topic, there you got it. There's a variety of other terms. I saw the Libby half-life versus the Cambridge half-life. You can investigate those kind of things. And anyway, that's 3.1, 3.2, and there's a bunch of stuff on carbon dating and that kind of stuff. Lots of things there. 3.2 is nonlinear models and modeling with those. And 3.3, modeling systems of first order differential equations. And I think that's it for Chapter 3. So it wasn't a very long chapter, but one that you might want to just glance through just to see if you'll need it in the future. We didn't have modeling in our course description, so we're skipping over it. However, higher order differential equations were mentioned, and that's where we're going to begin now. Chapter 4, we now turn to the solution of ordinary differential equations of order 2 or higher. In the first 7 sections of this chapter, we'll examine the underlying theory and solution methods for certain types of linear differential equations. The chapter concludes with a brief examination of solution methods for nonlinear higher order equations. I don't know if we'll get that far. Okay? Now, this first section, 4.1, again, they love to start off these chapters with sort of this general stuff, not giving you anything very specific. I guess the idea is to just give you a general concept of what you're dealing with. So often in my mind, it seems like this is just, I hate to say it, sort of like killing time. but that's not really what the intent is. But I like it so much better when they get down to specifics. So let's start with the general, and we'll try to keep it general as long as I can put up with it. And then what we'll do is move on to 4.2. So 4.1, preliminary theory, okay? This is calling back to what we did in section 1.1, page 57 in section 2.3. Recall that a general solution is a family of solutions defined on some interval I that contains all the solutions of the differential equation that are defined on that interval I. Okay? Now, 4.1.1 is going to deal with initial value problems and a look at boundary value problems. This is the first time we've seen boundary value problems, and we'll see the difference in them and initial value problems. Okay? We'll start with the initial value problem, which we're already used to, and then move to boundary value. Okay, so way back in section 1.2, we defined an initial value problem, IVP, for a general nth order differential equation. This is back when we're doing very general things again. Just right now we're finally doing higher order. Back then we were just looking at general stuff, nothing specific. Okay, so this is a linear differential equation of for a linear differential equation, an nth order initial value problem, IVP, reads like this. This is hopefully pretty much review. You have some coefficient function, a sub n of x, okay, times the nth derivative of y with respect to x n times, okay. Now, the n here indicates which derivative you're taking, okay. The n here is just the marker telling you this is the coefficient function that goes along with that nth derivative, okay. So then you'll have plus a sub n minus 1, also of x, times the n minus first derivative of y with respect to x, n minus 1 times, okay, plus, and they keep going, a sub n minus 2 of x, the n minus second. And in these cases, it's all right to put them like that. If you're using primes or numbers for primes, you put those in parentheses. We're not. We're doing the Leibniz notation, which is okay to write this way. dx sub n minus 2, okay? And they don't even put them in parentheses. Sometimes I think it makes them look a little easier to read. But anyway, keep counting down like that until you get down to your a sub 3 of x, and by that time you're down to the third derivative of y with respect to x 3 times, plus a sub 2 as a function of x times the second derivative of y with respect to x twice, plus a sub 1 with respect to x as a function of x, dy dx, plus a sub 0 of x. Okay? That is your differential equation side of it, and this is equal to some g of x. Okay. The right-hand side always has to be a function of x and x alone, as do each one of these coefficient functions. They're functions of x and x alone. No y's allowed in the coefficient functions or in the g on the right-hand side. Okay? They're functions of x and x alone. All your y dependence is located in your function y and your derivative of the function y. Okay, now that's the differential equation part. Here is your initial value part. Subject to y at x sub 0, some value x, we'll call it y sub 0. And then we'll have y prime at x sub 0. I'll put my 0 in the wrong place. Okay. Also at the same value of x, we'll call this y sub 1. And subject to y sub double prime at x sub 0 will be y sub 2. And y triple prime at x sub 0 will be called y sub 3. And we'll keep on counting down till we get y sub n minus 2. I think it goes to n minus, let me do n minus 3. Okay. The n minus first derivative of y. Now, notice down here, they put it in prime notation, which when you get past 3, you put it in parentheses. n minus 3 at the same value, x sub 0 is equal y sub, y didn't come out well, did it? Sub n minus 3. Y, the n minus second derivative of y at x sub 0 will be y sub n minus 2, and y sub n minus 1 evaluated at x sub 0 will be, wait, I'm going the wrong way. No, I'm going, yeah, will be y sub n minus 1. Okay, stop there. Okay, now notice how many you have. You have n derivatives in the upper equation, and how many initial value points do you need? 1, 2, 3, 4, all the way up to n. So you need n there as well. So it says, recall that for a problem such as this one, we seek a function defined on some interval I. That the interval has to contain this x sub 0, where we're doing our initial value, and it satisfies the differential equation and the n initial conditions. There's n initial conditions for the n derivatives that you have. However, notice those conditions, the initial conditions, they only go to the n minus first derivative. The reason for that is you have the y sub 0 down here, which is your y position at not a derivative but at the function. Y of x0 is equal to y0. Then all the rest of them correspond to the number of derivatives. And since you had n minus 1 derivatives here, you have n minus 1. When you add that next one, you can come out with n. So you do have n initial conditions for those nth order differential equation. Now, they say, recall for a problem such as this, we seek to find a function. We seek a function defined on some interval I that contains that. Okay, I think I already read that. We've already seen that in the case of a second order initial value problem, a solution curve must pass through the points x0, y0 and have a slope of y1 at that point. Okay, that's if you only had a second order, let's see, yeah, initial value problem. So they talk next about existence and uniqueness, and said back in section 1.2 we stated a theorem that gave conditions under which the existence and uniqueness of a solution of a first order initial value problem were guaranteed. The theorem that follows here gives sufficient conditions for the existence of a unique solution for the problem. Now I get to talking, let me make sure we're not running out of time. No, we've got about 18 more minutes. Okay? So, here's theorem 4.1.1, and I think I'll write this on a clean page just to keep me from running into the bottom where when you get into near these little icons down here, they sometimes mess up your print. So I'm going to erase the ink on this slide and give you theorem 4.1.1, existence of a unique solution. Okay, let's let a sub n of x, a sub n minus 1 of x, a sub n minus 2 of x, all the way down to a sub 3 of x, a sub 2 of x, and a sub 1 of x, and a sub 0 of x, and g of x. Okay, here's all your functions that are functions solely of your independent variable x. And every one of those has to be continuous. Okay? On the interval I, and your a sub n of x, that very first one there, cannot equal 0. Now, there is a reason for that. Same thing from way back in pre-calculus algebra. Okay? If a sub n was 0, that means your first coefficient is a 0, and then that wipes out your entire first term. So your nth derivative is gone. So it will not be an nth order differential equation if you don't have an nth derivative. So that's why you say that a sub n of x cannot equal 0. Okay? For every x in the interval. Now, if x is equal to this x sub 0, and that's any point on the interval, okay? Okay? Then a unique solution, y of x, of the initial value problem exists and is unique. Then this unique, then a solution y of x of the IVP, initial value problem, exists and is unique. I'm going to put exist on the interval on I and is unique. Okay. That's your existence theorem. All right. We're going to do example 1, which is not a very rigorous example. It's just an example. Okay. I'll erase this just in case I need more room. Here's your initial value problem. 3 times y triple prime plus 5 times y double prime minus y prime plus 7y is equal to 0. Now, how many initial conditions would you need? Third order, 3 initial conditions. Okay? And what could they be? Y at 1 is equal to 0. That's a perfectly legitimate one. But From now on, everything else has to be evaluated at 1. Won't necessarily have 0 as a solution, but it'll be a value. So y prime at 1, and they give us here of being 0 again, and y double prime of 1 is equal to 0 again. Now they just made those 3 equal to 0. You don't have to. This is a fairly simple case. Okay? Now, any third degree differential equation, third order differential equation, you're going to need 3 initial conditions. Okay? They all have to be at the same point. They don't have to be 1 or 0. They can be anything, but all 3. The function itself, the first derivative of the function, and the second derivative of the function. Notice we never get to the third order that you got in differential equation in naming that, because you started with that y of 1 is equal to 0, so you only need 2 more, giving you y prime and y double prime, not y triple prime. Okay. Now, they tell us this has the unique trivial solution of y is equal to 0. Well, of course it would. When y is equal to 0, that first term is going to be 0. The first derivative of 0 is 0. The second derivative of 0 is 0. The third derivative of 0 is 0. So all these added up are going to give you 0. And y at every value, 1 is equal to 0. Y prime 1 is equal to 0. And y double prime at 1 is equal to 0. Okay. Because it has this, y equals 0 is a solution, but the theorem above said if there is a solution, then, and it meets these criteria, then it is a unique solution. So it's the only solution you have on any interval that contains the variable 1. The value of the variable would be equal to 1. Okay. I'm going to, I hate to do this. We've only got 11 minutes left, 10 minutes left. I'm going to try to slug through example 2, but I can't remember. Yeah, I think both of you were here last week when I told you the results of my visit to the hematologist on Tuesday of last week, that I was basically very anemic. So it means I run out of juice really fast, which I'm approaching doing right now. Afternoons are worse than mornings. I can go pretty much in the morning, but afternoons get tough. But in addition to that, I found out, and this has nothing to do with energy levels or anything, I don't think anyway. Friday when I went by, I had a dermatology appointment, so I went by to pick up my labs from Tuesday because they had not put them on the portal where they said they were going to. When I picked those up, I found out also my immunoglobulins, that's the IgGs, IgMs, IG something else's, they are also very low, which means my ability to resist diseases, infections, and things like this is also pretty low. And that's concerning with this coronavirus coming up. And, I mean, folks, it's only a matter of time before it gets here, okay? So it could be at some point I might not be able to come in if we get a some sort of an outbreak of it, or any exposure of it probably. I'll probably be almost required to be quarantined at home. Then we'll go with the videos and things like this, and I'll try to be available to answer questions. I'll give you, you can email me and call me or whatever. So that may be coming. Hopefully we can get through this without that happening. We've been very fortunate not to have any cases, I don't think any in Alabama yet that we know of, possibly those two over in Jacksonville. So they may or may not develop into cases, but once it gets into an area, it kind of explodes. So we don't have as much moving around of people as some areas like New York and Seattle and places like that do, but we still have enough that it's going to move and probably move pretty fast. If we could just outlast it, if it is going to be seasonal and warmer weather gets here and it starts on the decline, we may escape the worst of it. There's no indication that's going to be the case, so we'll just have to see. So anyway, I'll talk too much right now. Let's see if I can get example 2 done. I think I'll erase what we've got here so you won't confuse it with example 1. It says you should verify that this function, y is equal to 3e to the 2x plus e to the minus 2x minus 3x is a solution for this initial value problem. This differential equation, y double prime minus 4y equal 12x. That's the differential equation. Here is the initial condition, y is 0 equal 4, and y prime at 0 has to be the same value. You've got a second order differential equation. You need 2 initial conditions. This will be it. The second one, y prime at 0 is 1. So all they said was verify it. Okay, so let's do that. Remember how we do that? Y prime would be 6e to the 2x minus 2e to the 2x minus 3. That's your y prime. Your y double prime would be 12e to the 2x plus 4e to the minus 2x. Stop. Okay? Now let's plug these back into our the differential equation, see what we get. 12e to the 2x plus 4e to the minus 2x minus, there is no y prime, so we go back to y. So this will be minus 3e to the 2x minus e to the minus 2x minus 3x is equal to $12x. There it is. I couldn't see it. 12x from right there. Okay. Oh, wait. Sorry, my phone's going off. That's why I don't like bringing my phone to class. Okay. Now, I got that part. What I missed was this part. It's minus 4 times y. So this is minus 12. Okay. Okay. Minus 4 times y, that would be a minus 12 e to the 2x minus 4 e to the minus 2x, and then you got a minus, so that's going to be plus 12x. Because you have a minus 4 times a minus 3 is plus 12x. Okay? Now, Let's see if that does indeed fit. Here's a 12 and a minus 12, a plus 4, a minus 4, and then 12x equal 12x. That certainly works, okay? The other thing to check is that our initial conditions are met. Well, when y is equal to 0, plug that in here. Y of 0 is equal to 3 plus 1 minus 3. No, minus 0. 3 plus 1 is equal to 4. That works. Let's see, when y prime is equal to 0, this will be y prime at 0 will be 6 minus 2 minus 3, which is indeed equal to 1. And that checks too. So both the differential equation fits, it works, and the initial condition works. Okay? Now, it says now the differential equation is linear. The coefficients as well as g of x equal 12 are all continuous. Our coefficients here were 1 minus 4, and the 12x is continuous. The a sub 2 is a 1, and that's equal to, it's not 0. And on some interval I containing x equals 0, because we were putting it in, these are good everywhere. We conclude from theorem 4.1.1 that this given function is a unique solution. It fits, all the conditions are met, that's where we have it. Okay? And it's 3:44, so I think we'll be starting next time right here, kind of in the middle of this page here. One time I had an eraser up here there, I found it. The erase where I started some other time. And we will pick up and go from there next time. Let me give you just a few, let's see if there's at least one or two. Wow, this is a long section. It has all these subsections in it. Yeah, 1 and 3 are a lot like what we just did. Given a family of functions as a general solution, find, okay. No, this is not quite like it is. It said, in these problems, the given family of functions is the general solution of the differential equation on the indicated interval. It says, find a member of the family that is a solution of the initial value problem. We didn't quite get so far as to do that yet. But you need to be able to do it. It's not going to show you anything special that's going to enable that, I don't think. So, well, maybe that next thing, the first thing we do. So if you don't want to work at either 1 or 3 yet, you can wait and do those next time. And but you got plenty to do from, what was it, 2.6. Okay, I think that was that was the section we picked up with today. All right, and that did bring us to, actually a minute over, but no extra charge here. So let's end the recording.